Okay,
So,
moving along now, we have Team Beca here. We have Adrian Dickison coming to us from New Zealand. Adrian is the technical fellow and co-founder of the program Maestro for Beca, and he's going to take us through that in just a moment. Joining him is Jack Timmings, also from New Zealand, going to help us out with some projects and what's been happening over there. And then we also have Graeme Harding joining from Becca's office in Melbourne. And for those of you who don't know Graeme has a very long history within renewables and sustainable design. And his time in Africa has seen him a little bit ahead of us because they've had some electricity issues and energy issues over the years, almost necessitating them to be absolutely world class when it comes to energy. And after doing many different projects within heat pumps and solar, it's going to be fabulous to hear from Graeme as well. But to kick us off, Adrian Dickison from Beca is going to take us through their platform that they have that's going to help optimize the performance of heat pumps. Adrian, over to you.
Thanks, Jared. And just in the same vein as the Australians tend to do now, I'll acknowledge that I'm in Tamaki Makaurau, Auckland, which is where the Ngāti Whātua are the tangata whenua. And without further ado, we'll talk about refrigeration and heat pumps. Okay, we've already seen who we are. And first slide, what is Maestro? Maestro is a machine learning algorithm control system. It has inbuilt digital twins for compressors, and it has a control schema which is always seeking to optimize the performance of a refrigeration system, and largely on the high side. So we're looking at the engine room performance, and that's largely associated with the compression and heat rejection part of the plant. And of course, that has a lead on into heat pumps, which we'll talk about later on. It's system and vendor agnostic, so it can run on top of any system, but really we're focused on ammonia screw compressors for the most part. And also just to comply with companies' IT requirements, we can run this as a totally air-gapped system. We don't have to talk to the outside world. That's one of the questions which comes up quite regularly. Just want to give a quick shout out to Michael Belstead and the AMPC. A lot of the work that you'll see here has been inspired by the work that they've done on energy efficiency. So for those of you who aren't in the meat industry, I would certainly recommend that you get into those documents and have a look at them. They've got some great stuff. It's really clearly communicated with great graphics as well. What is the special thing about Maestro that other places don't reach? Well, it's continuous optimization with varying load and wet bulb every 5 seconds. So what we know is that people are quite used to running refrigeration plants with reset of discharge pressure with respect to wet bulb temperature. But however, we do that for load and temperature because load's varying all the time in a typical process plant. If you're just resetting your wet bulb temperature several times a day, that's not going to cut it in terms of getting the absolute in energy efficiency. And you can see here, and this is sort of a typical plot of where the optimum might lie for a certain set of conditions. But there's clearly a dip which has a significant amount of energy saving associated with it. And just to add some solar flavour, since we're talking to a largely Australian audience, we did have the question, and I think it actually came from Jared a couple of weeks ago. When does Maestro save the most energy? And of course, the answer is at the beginning and ends of the day, because we are basically manipulating the capacity of the system that's available to us when load is not peak load with peak wet bulb. Obviously, if you're in the middle of the day when it's hot and you're processing a lot, you don't have a lot of margin in your system. It will be running close to capacity. So what we kind of do, I describe it as sort of, finding the coins under the cushions on the couch. And that kind of ties in quite nicely with where, you're going to be having higher fossil burn to generate your electricity in your market. And we can see that, our savings are on average in the zone 10 to 15%. Because we have digital compressor twins built into the system, we can look at the performance of the compressors. So we're basically comparing the actual performance with the vendors or the OEM's nominal performance. So you can see here that the expected power is along this barrier between the pink and the green zones. That's the Y equals X line, if you want to call it that. So that would be the expected power for a new compressor at a given condition. And we can see here that the actual compressor in this instance is running typically around about 125 kilowatts higher than the nominal, let's say 375 that you would expect in the brand new condition. And one of the things that we've seen is that people are very interested in doing data-driven maintenance that allows them to justify business cases with paybacks. So you could believe your refrigeration contractor when he says you need to rebuild a compressor, but here we can show, and this is coming out of Michael Belstead's AMPC documents, there is good cases in many instances to replace compressor blocks outright, simply because with a screw compressor you can't win back the power losses with let's call it a mechanical rebuild. The compressor on the right is part of the same system. It's a VSD compressor, and you can see at the top here we've got a bit of a cap on drawn power, and that's the VSD limiting power at high loads. In this instance, this compressor is actually more worn out at higher loads, and it's actually pulling at a nominal 300 kilowatts. It's actually pulling in reality another 150 kilowatts, and that's why it's maxing out on its motor. So this is a big thing. I think it's one of the unturned stones that's available to us in the refrigeration space. And in that same vein, when we're talking about heat pumps, I would say that we want to bolt a turbo onto a Porsche, not onto a Model T. So if you're going to put a heat pump on a refrigeration plant, make sure first that your refrigeration system is performing nominally and is well maintained. Some of the other characteristics of Maestro, because we're driving discharge pressure set points under our control schema, we get to see many things that you wouldn't normally expect to see just from the raw data in a fridge plant. This is just showing a trend of condenser fan power in 100 kilowatt of refrigeration buckets. And what you can see is that there's a significant change from 2022, which is the green data, to 2023, which is the red data, where we can see at many conditions, we are actually doubling the fan power. And that's telling us the extent of fouling that's actually preventing us from rejecting heat to atmosphere without working the fans harder. And in fact, in like-for-like instances of load and temperature, we're seeing an increase of 18% in the drawn power to reject that same amount of heat, do that same amount of refrigeration. In the same vein, air ingress, although it happens, it's not as insidious as fouling, and it happens episodically. We can also see immediately when air ingress is an issue, and that's really a function of purger performance if you have a purger. And what we know there is that under like-for-like conditions, the power increase under air ingress conditions is typically of order 28%. So, a significant penalty if you allow air ingress to continue for a sustained period. So what are the economic results? So this is from last year's operation of this particular site. The average refrigeration load is about 730 kilowatts. So the drawn power of this plant's around about 250 kilowatts typically. We saved, just with the Maestro schema itself, about $45,000 on 323, so that's about 14% of baseline. However, with the insights that we get, we can see that there's another almost the same amount of saving on the table just through correcting malaoperation and fouling. So malaoperation, we include running on the wrong compressor, so running on the fixed speed compressor instead of a variable speed compressor at low loads. Too many compressors running air ingress and fouling. So those two blocks make up those on the table available wins, and that would give us a Maestro target down here, which is something of order almost 30% savings. And then of course we can actually enumerate the compressor losses and show them as a power loss too. And in this system, it turns out to be about 8% of the baseline. So before I was talking about very high compressor power losses, but that's usually at high loads. This load, the plant is relatively lightly loaded, so the compressors don't work too hard, so you don't get the big gas losses from leaky compressors because you've got lower pressure ratios typically. So we can see here that the feasible target with new compressors and good operation is about 35% power savings. So significant improvements available. The next thing we wanted to talk about was some work we've been doing lately in looking at putting a heat pump over the top of a refrigeration plant. So the example I've got here, we've got a classical ammonia refrigeration plant with an evaporative condenser connected to a heat pump. It's connected in a cascade arrangement, not directly, and I would always prefer to separate the heat pump compressor and the ammonia gas from the refrigeration plant for reasons of oil hygiene, and I think many of the OEMs would concur with that. So nominal condensing condition 32 degrees, nominal evaporating condition for the heat pump 30 degrees, so 2-degree delta across that cascade condenser. And in this instance, we're talking about condensing at 70 on the heat pump to make 65 degrees C hot water. And what we've done is we've actually taken real refrigeration plant data running under Maestro, and we've put a simulation of a 500 kilowatt heat pump over the top. In this instance, it's a Micom high pressure reciprocating compressor. And so here are the results, and you can see that the results are kind of spiky because, in fact, when we're doing the simulation, we're sort of trading off cylinder loading and VSD speed as we manipulate the heat pump to produce the required COP or the required heat. What you can see here, the traces at the top are the COP in orange of the heat pump itself. Now, the reason we're looking at this is simply because we know that anecdotally, people are raising the discharge temperature of the refrigeration systems to make the heat pumps work harder, to improve the COP of the heat pump. Across the bottom of the graph here, we've got saturated discharge temperature for the refrigeration plant. And so the green trace is actually the overall COP. So that is the COP of the refrigeration plus the heat pump duty divided by the total power. And what you can see here is, in fact, to favor the heat pump by raising the saturated discharge temperature of the refrigeration plant, you're killing the overall COP. So you're going backwards. And the reason for that, and you can see here's the power trace, the trend of the power trace is going up from around 300 kilowatts, inevitably towards 400 kilowatts. And the reason for that is that as long as your heat pump is smaller than your fridge plant, the fridge plant COP dominates the calculation. So that's what you've got to take in mind. So bearing that in mind, what we did is we said, okay, that was 500 kilowatts of heat pump. What happens if we have different size heat pumps? So we built a family of curves here, but just to show that, and the salient point here is that all of the COP curves, irrespective of heat pump size, are sloping down. So basically, you're never winning by lifting the saturated discharge temperature of your refrigeration system to favor the heat pump. And just here at an optimum, what we call the Maestro optimum, which is what we've determined to be the optimum for this particular system, if we were to lift up from 23.6 degrees saturated to 28.9, we just use more power. And at 29.9, we use 8.5% more power. So the short answer here is don't do that. As long as your heat pump has got enough capacity, it must be slaved to the needs of the refrigeration plant. And that's my bit. Handing over to Jack.
Cool. Thanks, Adrian. We've touched upon a couple of really salient topics already. Getting your refrigeration plant tidy, the possibility for solar thermal systems to support high temperature heat pumps. I wanted to take this opportunity to walk you through an example of a heat pump project that I've just been delivering with Adrian's help and others from Beca for a food and beverage client in New Zealand recently. It's a project that we ended up working with the client through the full design process, and the project has recently been commissioned and has been operating very successfully for a number of months. So I thought I would sort of talk a little bit about how that design journey evolved over a couple of steps and some things to look out for in your own projects, with the sort of tagline: the better you understand your system, the better the final design and carbon abatement is going to be. So I'll go to the next slide. Thanks, Adrian. Awesome. So step number one, understand your hot side and your cold side, right? Adrian's point here, I think, is very salient. You need to make sure, I think, before thinking about putting a heat pump on top of an existing refrigeration system, that your existing assets are operating in a way that you would be comfortable with securing for the lifetime of the heat pump. Because putting a heat pump on top of or feeding into a refrigeration network or a hot water network kind of commits you in some ways to operating your assets in that kind of way for the rest of its useful design life. Otherwise, what you'll end up with is a heat pump that's either too big or too small, and capital that could have been deployed more successfully on other parts of the project or in other decarb initiatives across your business line, right? So in this example, on the cold side, when we started working with the client, the duty of the fridge plant that we had initially sort of thought would be a good idea to bang a heat pump on top of turned out to be a lot lower than anticipated due to operational changes that had happened in the plant over the last 2 to 3 years. Not an uncommon thing to see in the food and beverage world, but until we had put some temporary metering on the system, we didn't know that the flow rate, for example, in the cooling water recirculation loop hadn't changed, which meant that we were rejecting water to a cooling tower and bringing it back into the process with a delta T of kind of 1 to 2 degrees instead of 5 to 6, what the system was designed for. So in order to get so before we even thought about doing the heat pump, we spent a bit of time getting that refrigeration system working properly again. On the hot side, we found some other things, right? Some existing control issues in the hot water network for the plant meant that we were needing to artificially increase the designed or the intended hot water supply temperature to account for it getting lower and lower on its way to the users. So that made it more difficult and was going to be an efficiency barrier to installing a high temperature hot water heat pump. So we spent the time working with the operations plant to run some trials and lock in a control schema that enabled it to work with a more suitable hot water temperature. So those two things actually banked us a lot of savings before the project had even started. And I don't think I'd be going out on a limb here to say that similar kinds of opportunities are available to lots of similar operations, even without installing the heat pump. So the next slide, please, Adrian. So a couple of things that kind of surprised us in the data gathering stage for this project, but ultimately the complications that we identified were addressable, and there was still a good business case for the project. But I think in other situations, it's not until you've sort of thought about installing a heat pump that you might actually go out of your way to collect some of this operational info. So once it comes back together, I think one thing I would definitely say is this is a great time to come in and reevaluate your business case. Check your assumptions still stack up. Are you happy with what you found? Might there be some more work to do on your existing system before you move down the pathway to detailed design of the heat pump system as a whole? Cool. Next slide. Thanks, Adrian. So then after we knew we had our data in place and we trusted where it was coming from and we were happy with how the upstream and downstream systems were operating, now we move into cycling through our design options, right? Sizing our heat pump. We tested actually a number of 4 or 5 different heat pump sizes in a model, understanding what kind of waste heat we had available and what kind of heat demands there were on the site before we picked something. And what that kind of modeling exercise showed is that we reached a kind of critical point in which increasing the size of the heat pump, and which is more capital spend, actually didn't deliver us very much additional gas offset or carbon reduction opportunities. So, doing that exercise locked us, identified capacity that we didn't have to install, capital that we didn't have to spend, which was a good result for the project. Then we had a look at thermal storage, because this was something that was really going to help this project, because a lot of the time the refrigeration plant and the hot water system weren't sort of working eye to eye. They were operating at different times of the day. We had waste heat, but we didn't have a use for it, or we needed hot water, but there was no waste heat to access it. Thermal storage, I think, is a massive enabler for heat pumps to do more with less capacity, because it helps smooth out those operations if the hot and the cold side are out of alignment or one's less continuous than the other. So we ended up installing a low side thermal storage unit to allow us to bank up that sort of low temperature energy over the day, so that we could use it at night when the hot water system was really busy. And then we had to think about other heat sources as well, right? We discovered that this system was one where we could put in as big a heat pump as we wanted. Effectively, there was so much heat demand at that site that we weren't ever going to be able to totally get rid of the gas with just the refrigeration plant. So we had to start thinking about other options. We investigated actually partnering with a number of neighboring sites going forward when they had asset replacements that were coming up, so accessing waste heat from beyond the site boundaries. None of those opportunities lined up during the stage one project implementation scope, but we've talked to them about a couple of asset refresh opportunities in the next 5 years, which look really promising. But we did end up installing some solar thermal generation to work kind of in tandem with our refrigeration plant's heat rejection to increase the role that our heat pump could play. Next slide, please. So designing a heat pump together, from that point of view, is a lot like putting together a puzzle. And I think the most important thing to do is make sure you know the size and the shape of all of the puzzles you've got before you start trying to put them together, and also have an awareness of how new pieces might be able that you could bring into the puzzle, like other heat sources, thermal storage, optimizing your plant, could change the final picture that you build for the heat pump system itself. Next slide, please. So yeah, you'll see actually Adrian in one of the orange vests in this picture, but the project has been running for a couple of months now. I've put in a couple of choice photos of the heat pump skid provided by JCI. I think I see Ricky from JCI on the call today. We had some really great vendors come in and support us with the final design and delivery of this project. Here's a little picture of some of the solar thermal panels we installed, evacuated tube, evaporator panel type arrangement. And you can see there's the heat pump, and right next to it's the big thermal storage tank we put in. At the moment, the system's up and running. We've gotten rid of about 80+% of the existing or the previous gas utilization at the site, and we've improved a bunch of operability and reliability issues that the operations team have been working with. So, really cool story. Hopefully, some of the stuff I've talked about today has been helpful for people on this call who might be thinking about their own heat pump journey. But thanks for the opportunity to speak, and I'll hand over to my colleague, Graeme.
Good. Yeah. Hi, thank you. We are running short on time, so I'm going to go quickly through two case studies, building on what Jack and Adrian have been doing. So the first was a 2011 ammonia heat pump project. And at that stage, there certainly weren't package chillers available. I didn't have Adrian sitting around to tell me not to install it directly on the high side. So that's exactly what we did. And because I think we were only producing sort of 60-degree water, it has run quite successfully since then. So there's a lot to take in on this diagram. Firstly, I'll just talk you through the water circuit. That we installed a new condensing heat exchanger in parallel to the evaporative condensers. And so we preheated the water to about 30 degrees. And we then took that water through the heat pump, and then the heat pump only had to boost it from 30 to 60 degrees. And that condensing heat exchanger is a lot cheaper than a heat pump, so it made a lot of sense in terms of the overall performance. And then on the ammonia side, as I said, it was installed on the high side, basically taking the discharge from the compressors and boosting it up to sort of 60 degrees to condense at 60 degrees, produce hot water. And then that ammonia went into the common liquid receiver. So moving forward to the next slide, thank you. Here's some pictures. That's the condensing heat exchanger effectively boosting the condensing capacity. On the next slide, this is the heat pump. It was a reciprocating heat pump. I regret not being able to find any photographs from inside, but we got great performance out of it. The overall hot water COP was over 9, because of the preheating, although the COP on the heat pump was probably 6 or 7. And we had great data, and it's been running for many years since. If we can go to the next slide, please. As I said, we're obviously recording all the ins and outs and temperatures and power, so it was easy to calculate that. We've got a great overall COP. In the project, because we were competing with an electric boiler, we had a great payback, and it was about a 2.5-year payback at the time. And for the client, this was a chicken processing facility producing patties for Kentucky Fried Chicken. And the only thing that really we had to be aware of that caught us a little bit on that job was we needed at least 2 high-side compressors to run all the time to provide enough ammonia. And we did notice that when the heat pumps were running in the evening, we dropped the discharge pressure, and so their hot gas defrost didn't work so well. And so we had to move the hot gas defrost time, and then everyone was happy after that, and it's performed very well. This is a more recent study we just did, and this project is currently being installed in Queensland. And there we were also very keen to install heat pumps, but we needed a much higher temperature, and we obviously needed a lot of waste heat. So we modeled it throughout the entire year, and the red line is really the amount of waste heat that we required. And unfortunately, we didn't have enough. The bars below it are the sum of all the waste heats, available waste heat that we were trying to grab from all over the site. We didn't have this solar panel heating idea, although we did put solar on the roof. And there just wasn't enough waste heat, and combined with the fact that we really needed over 100 degrees, large amounts of over 100 degree hot water. And so we didn't go for a heat pump, and we did an overall, next slide please, life cycle assessment of all the options. We compared heat pumps, gas, electric, and for this particular case, a biomass hot water boiler was the solution that ended up being installed with an ORC, and that's currently being installed at the moment in Queensland. And that's me rushing through just the last few slides. Thank you very much for your attention.
Graeme, thanks so much for speeding through to get us a little bit back on schedule. I haven't seen any fresh questions come through. Let me just throw to Brendan. Any questions or observations there, Brendan?
I'm still digesting how much information we were just given in a short space of time. But I feel like I learned a lot in a short space of time. So I think the key takeaway for me was, and I come from a trade background, so making sure things are running properly should always be done, regardless of any upgrade you're doing. I think that's my key takeaway is you don't want to end up with something too small or too big that you're stuck with forever. So the importance of maintenance is always reigns supreme, I think. So.
Brilliant. And we've been asking that question over the last few years, actually, that Adrian's now answered about should you let that condensing temperature for the chiller the refrigeration plant start going up to try and help the heat pump? And looks like we got that question answered today. Thank you, Adrian. And that looks like, yep, no. In that scenario that you presented with every time the heat pump was smaller than the refrigeration plant, no, still optimized for optimal suction pressure and what have you for this. So maintain that floating pressure control for sure. So thank you, Adrian. And lots of other takeaways there. Yep, my brain is full of probably. I think I might need to watch the recording. Usually I don't need to watch the recording, but I think I'm going to need to watch the recording today. There's a lot coming at us there. So thank you so much there for our presenters.